Hello everyone, my name is Ali Salim. I am a PhD student at the University of Illinois at Chicago, and I am working with Dr. Ahmed Al-Khifa, the director of SWIM Research Lab. And today I am going to talk to you about how we developed a machine learning framework to identify contamination sources in serial networks. So let's start by defining the contamination source identification, in short CSI. So the problem starts by or after detecting a contaminant trace in the serial network, and we have a time series for the concentration of that contaminant with time. After that, there are two questions. The first one, where is the contamination location injection, and what was the injection pattern at that location? And we have to answer these two questions because the water quality in sewers impacts the wastewater treatment plant's performance and also the recipient water bodies. In addition, the solution of the CSI problem will facilitate in wastewater surveillance to track emergence disease hotspots and the consumption of illicit drugs. So, contamination source identification problem was broadly studied in water distribution systems, commonly in two approaches. The first one is the optimization approach by coupling an optimization technique with EBANet, or by the probabilistic approach to find the most probable solution. On the other hand, it was only studied once in the wastewater systems by coupling an optimization approach with SWIM. So our objective is to overcome the current limitations of these CSI models, as they assume conservative contaminant and they only deal with one contamination source. Also, they are very computationally expensive because they utilize the numerical model, which is in this case SWIM. So we will overcome these limitations by developing an efficient contamination source identification framework that is machine learning based. Actually, we are using multiple layer perceptual neural network, and it will be capable of identifying multiple contamination sources of active contaminants. So let's head to the methodology. We use the simulation optimization approach, which we couple an optimization tool with a simulation tool. The optimization tool suggests a certain solution, and the simulation tool simulates these solutions. And in this study, we use the genetic algorithm as the optimization tool, and instead of using SWIM, we use the neural network model that I'm going to explain in a while. So our workflow starts by utilizing and using PySwim, which is an interface of SWIM on Python, to train a training and testing datasets, and these datasets are then used to train the neural network model, so that the neural network model can get the relation between the input and the output. In this case, the input will be the contamination characteristics, and the output will be the simulation or the time series of the contamination concentration. This neural network model will receive the contamination events from the genetic algorithm, and it will send back the simulation results. And the mission of the genetic algorithm is to minimize the normalized root mean square error between the observed and the simulated contamination concentration. So you might think about the input of the CSI model. The input of the CSI model, again, is an observed concentration as a time series. And in this study, we reduced this observed concentration by simulating a known contamination event. And I mean by known is that we know the location of the injection point, the concentration at these injection points, the start time and duration of these injections. So for example, in this simple networks, the injection took place at 2 points. The first one was 15 milligram per liter. It started at 1 a.m. and it lasted for 5 hours. And by doing that, we can get the results at the outlet. So what we are going to do is we will feed back these results to the CSI model to check if it can predict and identify the location of the injection and the concentration of the injection, and also the start time and duration. So this is the overall idea. And we applied our framework on SWIM example 8 benchmark that has been used several times in the literature. This model has 6 subcatchments, 6 flow regulation units, 28 junctions, and 28 conduits. And we consider that every junction that receives a dry weather inflow can be a possible contamination source. And just to give you an insight about how complex the solution of this simple network is, this figure shows the sewage domain size on the y-axis as a log scale, corresponding to the number of contamination sources in this small network. For one contamination source, there will be more than 250,000 solutions, and for 2 contamination sources, this will reach 6 billion solutions. So getting the actual or the optimal solution from this huge sewage domain is a tough thing. In this study, we applied our framework on 3 testing scenarios. The first one, TS1, there was 2 contamination sources, and for TS2 and TS3, there was 3 contamination sources. So the difference between the first group that has this yes word here is that for TS1 and TS2, the number of contamination sources was known, whereas for TS3, the actual number of contamination sources was considered to be unknown, and I will explain this later at the end. So for each scenario, we have several cases. Each case will represent a different permutation of junctions. For example, if you are dealing with the first scenario, there might be a certain case where J1 and J12 is the 2 contamination sources, or J3 and J13, and so on. And also for each case, we applied our model 50 times so that we can calculate the 2 identification rate, which we are also going to see in a while. So let's go to the results. And because we are proposing to replace SWIM with the neural network model, we have first to check the accuracy of this model. And we found that the accuracy was equal to almost 1. And just for a random testing scenario, we can see here that the simulation results for the SWIM model and the multiple layer perceptual neural network was almost the same. And speaking about the time, the neural network model was order of magnitude faster than SWIM. And for one optimization run, it would take more than 3 days to complete, whereas for the neural network model, it only takes less than 30 minutes. So just to extrapolate this on the actual number of simulations I did in this study, it would take around like 80 years to complete this by SWIM, but like I am much younger than this, so so the realization of the neural network model could reduce the computational expense and actually maintain the simulation accuracy. So let's go to the actual results here. In TS1, and out of 6 billion alternatives, we were able to get the correct solution. And like looking deeper to the 2 identification rate, which actually I will explain now. For example, this number here, 66, this is the 2 identification rate at which the veil consisting of J12 and J1 is actually identified. So the interesting thing was that the 2 identification rate can be as high as 100% and as low as 32%. And also the interesting thing is that this matrix is asymmetric, which means that the 2 identification rate of the pair J12 and J1 is not the same as J1 and J12. And actually there's a reason for that. I just put that in the supplementary slides. If you are going to ask about this, I will show it to you, but I found that it's better to not say it here because it will take time. And what we are looking at right now is the 2 identification rate, but not for the pair. I am just speaking about the junction itself, regardless its pair. So in this matrix, the diagonals represent the diagonal represents the 2 identification rate, where in this junction, for example, J1 was the contamination junction, and J1 was also the detected junction. So what we can see here is that J3 was identified 100% of the time. So we related that to the residence time, and what we can see here is the residence sign of AUX3, which is actually the same as J3, is very distinct and unique compared to the other junctions. And on the other hand, the off diagonals represents the misidentification rate. And because J1 and J13 have the same or almost the same residence time, they were commonly misidentified with each other. So J1, when it was the actual contamination junction, it was misidentified with J13 and also the same thing. So what we talked about before was the location, and what we are looking at right now is the detected injection concentration. So the y-axis of this figure shows the detected concentration, but normalized with the actual concentration. So this value that equals to 1 means that the detected equals the actual. And on the x-axis, it's the contamination junction. And what we can see here is that the mean of the results shows that the CSI model was capable of identifying the actual concentration, and similar results were retrieved for the start time and duration. For TS2 and TS3, it's very hard to visualize the results, so we are just going to speak about the summary of the results. And for these two scenarios, 3 contamination sources exist. And for TS2, and out of 60 cases, the CSI model was capable of identifying 26, whereas for TS3, it was only capable of identifying 3. And this is why, because the actual number of contamination sources was considered to be unknown. Same results were retrieved for the concentration. The only difference between this figure and the one in the previous slide is that here the range of the detected concentration is much larger, which can be related to the added difficulty, because here we are dealing with 3 contamination sources. To conclude, the CSI framework is capable of identifying more than 1 contamination source, and the neural network model highly reduced the computational expenses and also maintained the accuracy. And the solution of the CSI problem is greatly impacted by the predefinition of the number of contamination sources. Thank you very much, and I look forward to answer your question. Thank you.
Yep. So, what type of contaminations are you looking at?
We are looking for the decaying contaminants, which is reactive or non-conserving contaminants, but not a specific contaminant by itself, because this is a framework that can be applied to any type of existing contaminants in serial networks.
Yeah, another comment. First of all, this differs from distribution system because most of the time it is a branch system. It doesn't have loops, so it should be relatively easy. That's just a comment. Another thing is, I think this can be very much applicable for finding sources of COVID.
Yeah, and this is what we said about finding the hotspot of the emerging diseases in epidemiology. Yeah,
that's the time. Yeah.
And that was actually the main factor of why we studied this specific topic, because it's very related to what we are currently facing.
Yeah, one last comment. On a level of 1 PhD, one dissertation, one PhD dissertation that we made in Italy, with trying to solve this same problem. So I can share it with you afterwards.
Yeah, is it in wastewater systems?
Yes, exactly. Solving the same problem.
Yeah, thank you. This is great.
Sure. Yeah.
I'm curious, what were the hydraulic conditions that you were solving? Like, were you having different rainfall inputs? Like,
yeah.
What were the hydraulic?
This is a very good question. And do we have time to show the supplementary slides, or
we really don't?
We don't. But actually, what we are representing here is the dry weather flow. We did the wet weather flow, but as you can see, we are very limited in time. But we considered both conditions. And we just assumed a certain rainfall depth with a certain pattern. That wasn't our focus, but we considered that.
Yeah. One last question right here.
Yes. Did you use the same neural network architecture for the optimization runs, or would you do
Yeah, actually I trained the neural network model so I can use it in the optimization runs. And because I trained the neural network model with a certain decay rate, and because the decay rate wasn't changed in the three scenarios, so we used the same neural network model.
Anyone wants to hang around after the session too? I think we're only have 4 speakers programmed, but we're welcome to stay after.
Thank you.
Thank you very much.